Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 29, 2026, just yesterday. It introduces a new framework that enables robots to manipulate moving objects in real time, boosting success rates in dynamic interaction tasks from a baseline of 21% to over 60%. The paper is titled DynamicVLA, a vision language action model for dynamic object manipulation. And as we'll see later, the specific architectural choices that allow for this speed are quite significant for the field. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 breaks down the latency challenge. In panel A on the top left, standard models suffer from what the authors call perception execution gaps, where the robot effectively pauses to process images before moving again. To solve this, panel B shows how DynamicVLA employs continuous inference, allowing the model to compute future actions simultaneously while executing current ones. At the bottom, panel C outlines the new dynamic object manipulation benchmark, where the radar chart reveals how this method outperforms baselines like SMOL versus LA and Flash across diverse interaction tasks. Figure 2 details the specific architecture and logic that make this real-time control possible. In panel A, on the left, the design combines a convolutional fast bit encoder with a truncated small LM2 backbone to keep the total size around 430 million parameters. Next, panel B illustrates continuous inference, where the system starts calculating future actions immediately, overlapping with current execution so the robot never pauses. Finally, panel C depicts latent-aware action streaming, which discards outdated actions that became stale during computation, ensuring the robot only executes commands that match the present moment. While Figure 2 details the model structure, Figure 3 presents the automated pipeline designed to feed it with data. On the left, the environment setup covers both simulation and real-world domains, utilizing diverse objects and varying lighting conditions. The middle column illustrates object state acquisition, where the system tracks position and velocity in real time to avoid the bottleneck of manual teleoperation. On the right, the state machine controller autonomously drives the robot through approach, grasp, and place cycles to gather data at scale. So, with the data pipeline established, Table 1 presents the comprehensive simulation results. It compares dynamic versus LA against baselines like Pi0 and SMOL versus LA across three main categories: interaction, perception, and generalization. If we focus on the interaction section on the left, specifically the closed-loop reactivity column, dynamic versus LA achieves a 60.5% success rate, vastly outperforming the runner-up at 21%. Moving to the far right, the average success rate confirms this gap, as the model reaches 47% overall, which is more than triple the score of any other method shown here. Moving from simulation to the physical lab, Figure 4 validates these findings with real-world experiments on the Franca and Piper robots. The top row displays success rates across 6 tasks, ranging from simple reactivity to complex sequencing, with the blue bars representing dynamic versus LA. On the far left, under closed-loop reactivity, the model achieves over 78% success on the coffee can task, effectively doubling the performance of the runner-up. As we look to the far right at long-horizon sequencing, the gap widens dramatically. While baselines struggle to reach single digits, dynamic versus LA remains robust, scoring over 71% on the tennis ball gathering task. Okay, Table 2 breaks down the model components through an ablation study. Rows 1 through 3 show that adding continuous inference or action streaming individually helps, but the final row confirms that combining them yields the best result at 47%. Interestingly, rows 4 and 5 reveal that bigger isn't always better. The 1.7 billion parameter model actually performs worse than the compact version, likely because its slower speed hampers reactivity. Finally, row 6 shows that removing the fast VIT encoder also causes a significant drop. Wrapping up, 2 takeaways stand out. First, handling dynamic objects requires speed, not just size. The compact architecture outperforms much larger models by prioritizing low latency over parameter count. Second, the introduction of continuous inference and latent-aware action streaming successfully bridges the perception execution gap, allowing robots to react in real time. This marks a pivotal step toward robots that can truly interact with a changing world. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.